A load brake switch alone is not an acceptable protection method for a transformer secondary. This is because a load brake switch lacks the capacity to interrupt the full fault current that could potentially flow through the transformer secondary during a fault condition. The absence of adequate fault current interruption capability poses a significant safety risk and could lead to equipment damage. An air circuit breaker, or ACP, equipped with a line-side ground, or LISG, is an acceptable protection method. An ACB with LISG is specifically designed to interrupt the full fault current and provide ground fault protection, ensuring the transformer secondary is safeguarded against a wide range of fault conditions. Omitting a main breaker and relying solely on a bus is also not acceptable. A main breaker is a crucial component for isolating the transformer secondary from the rest of the electrical system. In the event of a fault, the main breaker quickly disconnects the transformer secondary, preventing the fault from propagating further into the system and causing more extensive damage. Using two main breakers rated at 2500 amps each is an acceptable method, provided they are carefully coordinated to ensure both breakers trip simultaneously in response to a fault. This coordination is essential for maintaining consistent and reliable protection of the transformer secondary. The best option for safeguarding a transformer secondary is generally an air circuit breaker, or ACP, with a line-side ground, or a LISG. This combination offers the highest level of protection and reliability because it provides both overcurrent and ground fault protection, effectively mitigating the risks associated with various fault conditions. To elaborate further on transformer protection, consider the following aspects. Firstly, overcurrent protection is essential for safeguarding the transformer against excessive current flow, which can result from overloads or short circuits. Overcurrent protective devices, such as fuses or circuit breakers, are designed to trip and interrupt the current flow when it exceeds a predetermined threshold. Secondly, ground fault protection is specifically designed to detect and interrupt ground faults, which occur when current inadvertently flows to ground through unintended paths. Ground faults can pose a significant safety hazard and can also damage equipment. Ground fault protection systems typically utilize ground fault relays and sensors to detect and respond to ground faults. Thirdly, differential protection is a more sophisticated protection scheme that compares the current entering and leaving the transformer. If there is a significant difference between the two currents, it indicates an internal fault within the transformer, and the differential protection system will quickly isolate the transformer from the system. When selecting protective devices for a transformer, it is crucial to consider several factors. Firstly, the transformer's rated voltage and current must be within the voltage and current ratings of the protective devices. Secondly, the interrupting rating of the protective devices must be adequate to handle the maximum fault current that could occur at the transformer's location. Thirdly, the coordination of protective devices is essential to ensure that the devices closest to the fault trip first, minimizing the impact of the fault on the rest of the electrical system. Transformer protection also involves grounding practices. Proper grounding is essential for ensuring the safe and reliable operation of the transformer. Grounding provides a low impedance path for fault currents to flow back to the source, allowing protective devices to quickly detect and interrupt the fault. Ungrounded systems, on the other hand, can experience high transient voltages during faults, which can damage equipment and pose a safety hazard. The National Electrical Code, or NEC, provides specific requirements for transformer protection. NEC Section 450 covers the installation and protection of transformers, including requirements for overcurrent protection, grounding, and ventilation. Adherence to the NEC requirements is essential for ensuring the safe and compliant installation of transformers. Proper maintenance is also crucial for ensuring the continued reliability of transformer protection systems. Regular inspections, testing, and maintenance of protective devices are essential for identifying and addressing any potential problems before they can lead to failures. Maintenance tasks include inspecting the condition of circuit breakers, testing the operation of relays, and verifying the integrity of grounding connections. Moreover, surge protection devices, or SPDs, are often used to protect transformers from voltage surges caused by lightning strikes or switching operations. SPD divert the surge current away from the transformer, preventing damage to the insulation and other components. SPD should be installed at both the primary and secondary terminals of the transformer. In addition to the above-mentioned points, it's important to consider the impact of harmonics on transformer protection. Harmonics are non-sinusoidal currents and voltages that can distort the voltage and current waveforms. Harmonics can cause overheating of the transformer and can also interfere with the operation of protective devices. Harmonic filters can be used to mitigate the effects of harmonics. Furthermore, transformer protection must be coordinated with the protection of other equipment in the electrical system. Coordination studies are conducted to ensure that protective devices operate in a coordinated manner, minimizing the extent of any outages caused by faults. Coordination studies involve analyzing the fault currents and the time current characteristics of the protective devices. Let's look closer at air circuit breakers with line-side ground. Air circuit breakers, or ACBs, are a type of circuit breaker that uses air as the insulating medium to extinguish the arc that forms when the breaker interrupts a circuit. ACB are typically used in high-current applications, such as transformer protection. Line-side ground, or LISG, refers to a grounding scheme where the ground connection is made in the line side of the circuit breaker. This provides a direct path for ground fault currents to flow back to the source, allowing the circuit breaker to quickly trip and isolate the fault. ACB with LISG are capable of interrupting high fault currents and providing ground fault protection. In contrast, load break switches are designed to interrupt normal load currents, but they lack the interrupting capacity to handle high fault currents. Load break switches are typically used for switching loads on and off, but they should not be used for protection purposes. The selection of the appropriate protective devices for a transformer depends on several factors, including firstly, the transformer's kilovolt amps rating determines the amount of current that the transformer can safely handle. Secondly, the system voltage affects the voltage rating of the protective devices. Thirdly, the available fault current at the transformer's location determines the interrupting rating of the protective devices. Fourthly, the coordination requirements of the electrical system must be considered to ensure that protective devices operate in a coordinated manner. Transformer protection is a critical aspect of electrical system design and operation. Proper protection ensures the safety of personnel, protects equipment from damage, and minimizes the impact of faults on the rest of the electrical system. By understanding the various protection methods available and selecting the appropriate devices for the application, it is possible to achieve a high level of protection and reliability. Understanding the specific protection requirements for transformers is crucial for electrical engineers and technicians. Here are some additional technical considerations to ensure effective transformer protection. Firstly, inrush current mitigation is essential. When a transformer is initially energized, it can draw a large inrush current that can be several times its rated current. This inrush current can trip over current protective devices if they are not properly sized or set. Techniques for mitigating inrush current include using current-limiting fuses or circuit breakers with instantaneous trip settings that are above the inrush current level. Secondly, thermal overload protection is critical. Transformers can overheat if they are overloaded or if they are not properly ventilated. Thermal overload relays can be used to monitor the transformer's temperature and trip the circuit breaker if the temperature exceeds a safe level. These relays are often embedded within the transformer windings to directly sense the winding temperature. Thirdly, voltage regulation should be considered. Maintaining proper voltage levels is essential for the reliable operation of equipment connected to the transformer. Under-voltage and over-voltage relays can be used to monitor the voltage and trip the circuit breaker if the voltage falls outside of acceptable limits. Fourthly, restricted earth fault, or REF, protection is used to detect earth faults within the transformer windings. REF protection is particularly useful for detecting faults that are close to the neutral point of the winding, which may not be detected by conventional overcurrent protection. Fifthly, dissolved gas analysis, or DGA, is a diagnostic technique used to monitor the condition of the transformer oil. DGA involves analyzing the gases dissolved in the oil to detect signs of insulation degradation or other problems. The integration of smart grid technologies also influences transformer protection. Smart grids enable more sophisticated monitoring and control of electrical systems, including transformers. Smart grid technologies can be used to improve transformer protection by providing real-time data on transformer conditions, enabling faster fault detection and response, and facilitating remote control of protective devices. Additionally, the design of the transformer's cooling system is an important factor in its overall protection. Adequate cooling is essential for preventing overheating and ensuring the long-term reliability of the transformer. Transformers can be cooled by various methods, including air cooling, oil cooling, and water cooling. The choice of cooling method depends on the size and application of the transformer. The environmental conditions in which the transformer operates can also affect its protection requirements. For example, transformers operating in harsh environments, such as those with high humidity or corrosive atmospheres, may require additional protection against corrosion and other environmental factors. Special coatings and enclosures can be used to protect the transformer from these environmental hazards. The increasing use of renewable energy sources, such as solar and wind power, is also impacting transformer protection. Renewable energy sources can introduce voltage fluctuations and harmonics into the electrical system, which can pose challenges for transformer protection. Advanced protection schemes and harmonic filters may be required to mitigate these challenges. Furthermore, the aging infrastructure of many electrical systems is a growing concern. As transformers age, their insulation can degrade, increasing the risk of failures. Regular inspection and testing of transformers are essential for identifying and addressing any potential problems before they can lead to failures. When implementing transformer protection, it is crucial to follow industry best practices and standards. Standards such as the Institute of Electrical and Electronics Engineers, or IEE C37 series, provide guidance on the design, testing, and application of transformer protection systems. These standards cover various aspects of transformer protection, including overcurrent protection, ground fault protection, and differential protection. The coordination of transformer protection with upstream and downstream protective devices is essential for ensuring selective tripping. Selective tripping means that only the protective device closest to the fault will trip, minimizing the impact of the fault on the rest of the electrical system. Coordination studies are conducted to determine the appropriate settings for the protective devices to achieve selective tripping. Also, regular training of personnel involved in the operation and maintenance of transformer protection systems is crucial. Training should cover the principles of transformer protection, the operation of protective devices, and the procedures for responding to faults. Well-trained personnel are essential for ensuring the safe and reliable operation of transformer protection systems. In the context of industrial facilities, transformer protection is often integrated into a comprehensive power management system. A power management system provides centralized monitoring and control of all electrical equipment in the facility, including transformers. This allows for optimized operation of the electrical system and improved response to faults. The use of digital relays has revolutionized transformer protection. Digital relays offer several advantages over traditional electromechanical relays, including increased accuracy, improved reliability, and enhanced communication capabilities. Digital relays can also provide advanced protection functions, such as adaptive protection and fault location. Moreover, proper documentation of transformer protection systems is essential for maintenance and troubleshooting. Documentation should include single-line diagrams, protection settings, relay settings, and test reports. This documentation should be readily available to personnel involved in the operation and maintenance of the transformer protection system. For transformer protection in distribution systems, it is important to consider the impact of distributed generation, or DG. DG sources such as solar panels and wind turbines can inject current into the distribution system, which can affect the performance of protective devices. Coordination studies should be conducted to ensure that the protection system is properly coordinated with the DG sources. The concept of arc flash hazard is also relevant to transformer protection. Arc flash is a dangerous electrical explosion that can occur during a fault. Arc flash studies are conducted to determine the potential arc flash hazard at various locations in the electrical system. The results of the arc flash study are used to select appropriate personal protective equipment, or PPE, for personnel working on or near energized equipment. Transformer protection is a complex and multifaceted topic that requires a thorough understanding of electrical engineering principles and practices. By considering all of the factors discussed above, it is possible to design and implement effective transformer protection systems that ensure the safe and reliable operation of electrical systems. Lastly, the ongoing advancements in technology continue to shape transformer protection. New protection schemes and devices are constantly being developed to address the challenges of modern electrical systems. Staying abreast of these advancements is essential for electrical engineers and technicians involved in transformer protection.